Good day everyone, my name is Muhammad Rishad bin Moshidi. I am from the S125C and I am with...
Hi, my name is Muhammad Darwishi Irfan.
My name is Muhammad Arif Ilmi.
Hi, I am Kesli Rayanvadi from AS1205C.
And today we will present a presentation about gas chromatography and high performance liquid chromatography.
What is gas chromatography? Gas chromatography is an analytical separation technique that analyzes compounds eluted from the column, which carried through the column by a gas mobile phase. Gas chromatography differs from other forms of chromatography in that the mobile phase is a gas and components are separated as vapors. It is thus used to separate and detect small molecular weight compounds in the gas phase. The sample is either a gas or a liquid that is vaporized in the injection port. The mobile phase for gas chromatography is a carrier gas, typically helium because of its low molecular weight and being chemically inert. The pressure is applied and the mobile phase moves the analyte through the column. The separation is accomplished using a column coated with a stationary phase. Next, we move to the main principle of gas chromatography. The sample of analyte is introduced by syringe injection into the heated injected tube, where it is vaporized and mixed with the carrier gas. As the sample vapor or carrier gas mixture flows onto the column, the analyte partitions between the gas and liquid phases according to the analyte's component solubility in the liquid at column's operating temperature. This equilibrium partitioning continues as the sample is moved through the column by the carrier gas. The rate at which this sample travels through the column is determined by the sample's solubility in the stationary phase, the carrier gas flow rate, and the temperature gradient applied. Each component travels at the characteristic rate, and if the column has sufficient length and resolving power, the sample will be completely separated by the time it reaches the detector. Gas chromatography is mainly composed of carrier gas, which in this experiment is nitrogen gas, sample injection system, separation column, oven, detector, which in this experiment we use FID detector as it is suitable to detect hydrocarbon and exhibit high sensitivity. The objective of this experiment are to determine the retention time of N-butanol and 2-propanol. Number 2, to identify the component present in a standard mixture based on the retention time. And number 3, to identify the component present in an unknown sample. The apparatus and chemicals are as follows. Apparatus: syringe, beaker, and dropper. Chemicals: 2-propanol and N-butanol.
Next we proceed to the procedure of the experiment. Step 1. Sample handling. The syringe was rinsed before it was filled with the sample. The volume of the sample might be more than the required volume, so to make sure that there are no bubbles in the syringe must be tapped gently. The syringe was held vertically, needle up, and the plunger was pushed until required volume at eye level. The excess sample was removed using a tissue. Step 2. Sample injection and vaporization. The syringe filled with the sample was positioned in the hot injection port of the gas chromatograph and then it was injected quickly. The injection of the sample is considered to be a point in time because it is assumed that all and entire of the sample enters the gas chromatograph at the same time, so it must be injected quickly. The temperature was set to be higher than the boiling point of the components of the mixture so that the components will vaporize. The vaporized component then mixed with the inert gas mobile phase to be carried to the gas chromatographic column to be separated. Step 3. Separation in the column. Components in the mixture are then separated based on their ability to absorb on or bind to the stationary phase. The component that binds the most strongly to the stationary phase will spend the most time in the column, which means that they will have the longest retention time and they will emerge last from gas chromatograph. Meanwhile, the component that bind weakly to the stationary phase will spend the least time in the column and will have the shortest retention time, which means that they will emerge earlier from gas chromatograph. Step 4. Detecting and recording results. The component of the mixture will reach the detector at different times due to differences in the time they are retained in the column. The component that was retained the shortest time in the column will be detected first, while the component that retained the longest time in the column will be detected last. The detector sends a signal to the chart recorder, which is up in a peak on the chart paper. The component that is detected first will be recorded first, and the component that is detected last will be recorded last. Here is the overall data of the experiment. By using chromatography, the retention time of every chemicals were able to be determined. From the table, we can see that due to its retention time, the unknown sample was determined to be 2-propanol, as the retention time is closer to the observed retention time of 2-propanol in the standard mixture.
HPLC, known as High Performance Liquid Chromatography, is basically a high improved form of column chromatography. Instead of a solvent being allowed to drip through a column under gravity, it is forced through under high pressures of up to 400 atmospheres. That makes it much faster. It also allows you to use a very much smaller particle size for the column packing material, which gives a much greater surface area for interactions between the stationary phase and the molecules flowing past it. This allows a much better separation of the components of the mixture. The other major improvement over column chromatography concerns the detection methods which can be used. These methods are highly automated and extremely sensitive. Confusingly, there are two variants used in HPLC depending on the relative polarity of the solvent and the stationary phase. In normal HPLC, the column is filled with tiny silica particles and the solvent is nonpolar. Hexane, for example, the typical column has an internal diameter of 4.6 mm and maybe less than that, and a length of 150 to 250 mm. Polar compounds in the mixture being passed through the column will stick longer to the polar silica than nonpolar compounds will. The nonpolar ones will therefore pass more quickly through the column. In reverse phase HPLC, the column size is the same, but the silica is modified to make it nonpolar by attaching the long hydrocarbon chains to its surface, typically with either 8 or 18 carbon atoms in them. A polar solvent is used, for example, a mixture of water and an alcohol such as methanol. There will be a strong attraction between the polar solvent and polar molecules in the mixture being passed through the column. There won't be as much attraction between the hydrocarbon chains attached to the silica, which is the stationary phase, and the polar molecules in the solution. Polar molecules in the mixture will therefore spend most of their time moving with the solvent. Let's move to the procedure. For caffeine standard preparation, 10 mg of caffeine is weighed and is transferred into a clean 100 ml volumetric flask. It is diluted to the mark with HPLC grade water and shook to ensure adequate mixing. Filter the solution and it is filled in a vial with appropriate volume and is labeled. For Coca-Cola sample preparation, 200 ml of Coca-Cola drink is poured into a beaker and is placed in an ultrasonic cleaner to decarbonate the drink. 5 ml of Coca-Cola is pipetted into a dry 50 ml volumetric flask and is diluted to the mark with HPLC grade water. The solution is filtered and a vial is filled with appropriate volume and is labeled. For preparation of sequence samples, put the standard caffeine sample solution and Coca-Cola samples in the slots of autosampler and sequence template to make sure that the samples are in the correct slots. And run sequence is clicked. After some time, the data are printed.
From this experiment, we can determine the amount of caffeine in soft drink sample. Based on the graph of caffeine peak, obtained is 0.781. Therefore, Coca-Cola have caffeine in it because it has the same peak value with caffeine that measured in solution B, which is 0.781 using high-performance liquid chromatography instrument. In conclusion, there are 4 types of compound that are suitable for analyzing using HPLC, which is sugar, pesticide residues, organic acid, and lipids. How to differentiate between HPLC and GC in terms of mobile phase and columns. In terms of mobile phase, HPLC use solvent as mobile phase, while GC use gas as mobile phase. In terms of columns, HPLC using analytical column and guard column, while GC use pack column and capillary column. In conclusion, we are able to determine the retention time of standard solution in Coca-Cola and 100 plus soft drinks. We are also able to identify the caffeine peak in both soft drinks using the response factor method. By doing this method, we found out that soft drink, which is Coca-Cola, contain caffeine.